Okay, guys, I apologize for that. My camera stopped in the middle, so it's on 10-minute blocks, it seems, so I'll have to fix that later. But I think what we had here was that we figured out what our approximation was, right, for our derivative f prime of x, right? And we found out that the absolute error cannot be any bigger than f double prime at z times h divided by 2 factorial, where z maximizes my second derivative on the interval from x to x plus h, right? We have x to x plus h is going to be our interval that we're going to be approximating, using for our approximation of our derivative, right? And so this is where we left off. And so the question becomes, okay, here we use, so here we have our function. Suppose this is my function. Here I have the value x, and I have x plus h along the x-axis, right? And we want to be able to approximate our derivative, right, using these two values of x, right, along the x-axis, right? So we're using essentially the secant line, slope, to approximate the slope of my derivative, right? So here, my derivative at x. So here is my tangent line. So we're using the slope of the secant line to approximate the slope of the tangent line, right? And you've seen this in calculus all the time. Now, what makes this a little bit more interesting is that we are able to figure out what the error bound is, and we weren't able to figure that out before. And another thing is, you're like, okay, here I use x and x plus h. Can I use different values besides just x and x plus h? And sure you can, right? So suppose we want to be able to do that. Before we do that though, let me give a name to this particular approximation, right? So let's give it a name. We call this the forward difference formula if h is greater than 0. And we call this the backwards difference formula. This formula that we have right here. If h is less than 0, right? If h is less than 0. So it's called the forward difference because we're adding a positive value to x, right? Forward in time, you can think about it like that. It's called the backward difference, and we're taking away from x, right? So we're moving our x minus, it'll be essentially x minus h, right? Where if h was a positive term. So we're going to the negative, right? So we have the forward difference formula and the backwards difference formula. This is kind of the name for this. So let's go back to what we were saying before. Let's choose different values. So let's choose x and x plus 2h to approximate f prime of x. Okay. Let's choose. To be able to do that, I'm going to do the same thing I did before. Here I use the Taylor approximation, Taylor series of f of x plus h. Here I'm going to use the Taylor series of f of x plus 2h. Taylor series of f of x plus 2h. Okay. So f of x plus 2h now, it's going to look very similar to what we have here, right? Instead of using h, we're going to use 2h instead. So wherever I see an h, I replace it with 2h. So f of x plus 2h equals f of x plus f times x times, here I have h, I'm going to replace it with 2h, plus f double prime of x divided by 2 factorial times, here we have 2h squared instead of h squared, plus f triple prime of x over 3 factorial times 2h to the 3rd power instead of h cubed, right? Plus dot, 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 dot. Now the question is, can I approximate f prime of x, right, using the Taylor series of f of x plus 2h? And the answer is sure I can, right? Here I can do the same thing I did over here where I can say I'm going to solve for f prime of x. I have f prime of x right here. I'm going to solve for f prime of x. I'm going to solve for f prime of x. If I solve for f prime of x, I get this. F prime of x times 2h, right? Get f prime of x times 2h by itself equals f of x plus 2h minus f of x. Right. Same thing I did right here in this example, right? I'm going to do minus f double prime of x divided by 2 factorial, 2h squared, minus f triple prime of x divided by 3 factorial, 2h cubed, and so on. Okay. Now notice that the first two terms don't have any h's that are being multiplied times them, right? So when I divide by 2h, I'm going to divide this entire thing, these two terms by 2h together. They're going to come as a package. So I have the f prime of x is equal to f of x plus 2h minus f of x, all that divided by 2h, minus, now I'm going to divide this one by 2h. I get f double prime of x divided by 2 factorial times 2h. Because when I divide by 2h, one of these 2h's is canceled, right? Minus f triple prime of x divided by 3 factorial times 2h squared now, right? That's divide out one of the 2h's. So now this guy right here is going to be my approximation, right? Essentially, I'm going to approximate f prime of x using these two values, f of x plus 2h and f of x divided by 2h. That's going to be my approximation. And what's going to be my error? My error is going to be here, right? This is my error. How big does this error become? Well, the biggest it could be, just like we did over there, it's going to be less than or equal to the absolute value of, let's look at this term right here, f double prime, evaluate z, divided by 2 factorial times 2h. This guy right here. Where z is going to be the value that maximizes my second derivative from x to x plus 2h instead of x to x plus h, right? But then I say, wait a minute, I really don't need this 2, right? This is 2 factorial, this is 2. Really, I don't need these 2's at all. So I can really write this as just f double prime of z times h. That's as big as my error can be for this approximation. Okay. And I want you guys to notice that this approximation error is twice as large as this one, right? Here we divided by 2, right? So this is the only difference, right? This one's divided by 2 and this one's not. And that makes perfect sense because what? X plus 2h is twice the distance away from x than x plus h was, right? So we're going to compound our error. We're going to make it twice as big, right? So this is why this error is actually half the error of this approximation that we have right here. Okay. So this is we've actually made our approximation worse, right, by using x and x plus 2h. That's no good. And the question is, can we make our approximation better, still using just 2 points, right? Can we make our approximation better? And the answer is yes, we can. We're going to do that next, right?